Okay, YouTube, in my last couple of videos, we've been solving exponential equations. In this video, we're going to solve logarithmic equations. We're going to do it using two separate properties of logarithms, but let's go ahead and start by considering what we see here on the left. We have an equation here. It says log base 5. You'll notice that the variable expression is actually inside of this logarithm. So we can't just, divide both sides by log base 5, seeing as how log base 5 is a function, So we're going to have to do something here to undo this function here, which is, of course, use an inverse function. But essentially what we want to do, first things first, is this. We want to isolate the log. Okay, so isolate the log if possible. I'm going to write if possible, as a matter of fact, because this next example we look at here, it's not possible. But once we have this isolated, what we're going to do is we're going to ask ourselves, can we use the 1-to-1 property to solve this? Okay. As a matter of fact, I'm going to bypass that one, and I'm going to go straight to number 3 here, which is use the inverse property of exponents. And essentially what this inverse property of exponents is, it says if you had some expression like b, let's put it this way, we say log base b of some x, and this was equal to some constant, then think about what this expression is really saying here. It's saying that since I'm a logarithm, then in exponential form I would have some b that turned into x, essentially. It would turn into x by taking it to the power of c. And what we're going to be doing now is essentially using a property that says, well, if we were to take both sides of this expression, both sides, and raise it, and make it to the exponent, remember that the one-to-one property essentially says this: two things with the same bases, their exponents must be equal. Well, it would be likely, just likewise, it would be true. If two things are equal, then we can make them the exponents of a common base. The idea is that I'm going to take both sides, and I'm going to make both sides the exponent of some common base. On the right side, I have this c right here, and on the left side, I have log base b of x. And the idea is that when you take an exponential equation, exponential expression, to a power containing a logarithmic expression, and these have the same bases. Notice that they have the same bases here. And those cancel out, okay? And what you get left with is just the x here, and we have b to the c on the right. And this is the reason why I wrote this in exponential form first, is because basically I want you to see that they're the same thing. Excuse me. The idea, though, is this. We're going to be using the inverse property. And the inverse property that we used right here, basically what we did was we made both sides the exponent of some common base. So when you make this a common base on both sides and you make both sides the actual exponent, what we do is we have this name that we call this. We call it exponentiation. And when you exponentiate both sides, it's like saying we have this expression up here. By the way, number 1, isolate the log. It's already isolated on the left side. Since we can't use the one-to-one property, which I can talk about over here, let's look at number 3 here. It says use inverse property of exponents. And basically what we're going to do here is we're going to say, well, I've got a log base 5. How would I want to rewrite this expression so that it's still equality, but I can undo our logarithmic expression? We're going to use an exponential thing. And I'm going to use explicitly exponential things with a base of 5. So essentially we are going to exponentiate both sides, and that means that we're going to make both sides the exponents having some common base. So now I get this right here, and essentially what I can tell you is that those two things cancel out. Exponential things and logarithmic things are inverses, and these have the same basis. They have to. But what we get is this. We get 3x plus 1 is equal to 5 to the second power. And I also want to talk about why this is a reasonable expression. Essentially, we're saying that 5 is our base here. 5, there's your base, to the power of this thing right here turned into 3x plus 1. So 5 turned into 3x plus 1 by taking it to the second power. And the nice thing about this is once we've used that inverse property, check out what you get left with is a really simple algebraic equation to solve. This is a two-stepper. So we say 3x equals 24, and so it follows that x is equal to 8. And, what I want to do is I want to check this also. We say log base 5 of 3 times 8 plus 1 is equal to 2. Well, this gives us log base 5 of, let's see, 3/8 is 24 plus 1 is 25 equals 2. And I think that this is a very true statement. As a matter of fact, I say 5 to the what power equals 25? Well, 5 to the second power. So what we're going to do over here on the right is slightly different than what we just did here on the left. And what I can tell you is on the left, at least, this is a little bit more common, I would say. This is a bit more common. You have a log, you want to get it by itself, and you want to use the inverse property of exponents to undo the log. In certain situations, though, we have this one-to-one property of logarithms that basically says for positive numbers b, x, and y, and the base is not 1. We say two logs having the same basis. If you have two logs in an expression, sometimes it's beneficial to put one log on one side and the other log on the other, because look, if log base b of x was equal to log base b of y, then we could say with 100% accuracy that x and y must be the same things. So every once in a while you'll come across an equation that looks like this one here. It says log base 3 of 5x minus 1 is equal to log base 3 of x plus 7. This is very nice. As a matter of fact, I can tell you instantly that this must be true, that 5x minus 1, whatever that is, has to be equal to x plus 7, because otherwise, for all intents and purposes, these expressions are identical. So solving this now, we're going to solve this just like an algebraic equation. Let's go ahead and do that. We say 5x is equal to x plus 8. I'm going to go ahead and subtract this x from this side here, and we get 4x is equal to 8 then. And so it follows that x is 2, and we do want to check this. Always check your solutions. So in the original expression up here, we had log base 3 of, and this would be 5 times 2 minus 1. And this is log base 3 of x plus 7. So we have 2 plus 7 on the right. And so, in other words, this simplifies into log base 3 of 10 minus 1 is 9, and log base 3 of 7 plus 2, well, that's 9. So without even having to evaluate these, we say we get the same thing. But with evaluating these, remember that 3 to the what power equals 9? Well, that'd be 2. So we get 2 is 2, essentially. But that's how you solve a logarithmic expression. You either use 1-to-1 if possible, if you have 2 or more logs, drop them on either side, or use inverse property of exponents. Cheers.